which is the strongest base of these four compounds? Okay, so what are we going to want to do? So let's think about just what acids and bases are, right? HA in equilibrium with H plus and A minus, right? So stronger base means that this equilibrium favors the side of the conjugate acid, right? So what that means in terms of equilibrium is that this guy is unstable, right? So it has an ability to pick up this proton and go over here because this is at a really high energy, okay? So we can look at these guys, try to figure out which ones, rank them in terms of stability, and determine which one's basically going to most want to pick up a proton. So right, we can show this through resonance structures, which I will do, or you can try to remember a few, kind of simple things. So there's these aromatic ring, benzene rings. Okay, there's activating and deactivating substituents. So activating substituents will decrease the pKa. For example, this is an activating substituent. I'll show you why in a second with resonance. But what it does is it adds electron density to this, so through resonance, and so that puts more minus charge on the other substituents in the benzene. Okay, and so that, let's see, that would decrease the pKa, and it would increase the basicity. So this, I would think, would be the best base, right? This is a deactivating substituent. Okay, so that decreases the pKa, increases the strength of an acid because it pulls electron density away from this ring, away from the other substituents there, right? So basically, okay, you can go through the table in your book and memorize activating and deactivating substituents, and which ones are most deactivating, which ones are most activating, which one's a little less activating, and do all that, and just go through, based on that, determine which is strongest base. Or, if you don't want to memorize, which is the way I go about stuff, you can just show it real quick. You can think about it through resonance. Okay? So this guy, let's see, we'll have one lone pair of electrons that are going to want to pick up a proton, that are going to be available to pick up a proton, right? So basically, the resonance structures for N would be donating an electron there and putting a minus charge there. So we could put, that would put a double bond here and a positive charge on the end, lone pair there, and a minus charge, right? So that's the best we can do with A. Okay, so basically, the more, let me think about this, the more minus charge we put on N, right, so N, it wants to pick up a proton. Okay, you can think about it like that too. So the more minus charge that it has, the more it's going to want to pick up a positive charge, right? So we destabilize it with the minus charge, but we're adding a positive charge to it. You know, you can think of it like that. So here, right, just the benzene ring in itself pulls electron density away from the N. Okay, so let's see this O though, right? What would we do? We'd go here. We could go then here, and then we could go. Well, I don't want to break the octet rule. 1, 2, 3, 4. Right, so we're good there? Yeah. So what we did is we put a double bond here, and a double bond here. 1, 2, 3, 4, 5, 6 on nitrogen. So now minus charge, right? So this resonance form would do a great job of picking up an H+, right? So we made it we showed it's less stable than the others. It's going to be good at picking up this H+. So this guy, NO2, what does it look like? easiest way to draw it, O minus new plus here. Okay, so right, we could go, this guy is going to make this more positive, right? Because it's going to go here, here. Then after we do that, let me see, we could go here and here, right? So we added a double bond here, here, here. So we got rid of this positive charge and we added a positive charge here, okay, to that resonance. So that's, right, not going to want to pick up a proton that badly. So this guy right there with halides, right, it has a lone pair, so you might think you can go like that with resonance, but it really doesn't do that. We look at, with the halides, just inductive electron withdrawal and donation, because this is electronegative. The halides are electronegative, so it pulls a little electron density away from the benzene ring. So halides are slightly deactivating substituents, as we said at the beginning. Slightly deactivating substituents will be, the more deactivating, the lower the pKa, the stronger the base. But it's not as deactivating as this guy. It's not as activating as this guy. This is the most activating, right? It adds the most electron density to this N, making it the least stable, making it most likely to pick up a proton. In the end, these are